All right, now we're going to look at how to graph log functions. So here's an example where we have just y equals log base 2 of x, and it says to state the domain and the range. So let's just think about this in terms of starting from scratch and just thinking about an x and a y chart, right? So we already know that 2 is our base for this logarithm. That's already chosen for us. The thing that we have an option to plug in for here is this x. So what can we plug in for x and get an output? Well, if you think about this, can we plug in 0? Here's a question here. Can I plug in 0? So if I plugged in 0, what would my y value be? Well, you would be asking yourself the question, 2 raised to the what? 2 raised to the y value is equal to 0. Well, think about that for a moment. 2 to the what is equal to 0, right? And you shouldn't be thinking about anything because there is no exponent that if you take 2 and raise it to that number, it's going to give you 0, right? So this doesn't exist. You might be thinking, well, what about 2 to the 0? That doesn't work because anything to the 0 is 1, right? That can't work. What about just a negative number? Well, 2 to the negative 1. Well, that's not 0 because that's just 1 over 2, right? It's 0.5. It's closer to 0. What if I take 2 to the negative 10? Well, that's not 0 either. It's 1 over 2 to the positive 10. It's really close to 0. It's like 0.0000 whatever. But it's impossible to actually equal 0 here. You can't take a number, raise it to an exponent, and get 0. In other words, if you take any base, you can't keep multiplying by that base over and over again and somehow get 0. Because in order to get 0, you have to multiply by the number 0. So anyway, kind of a long-winded explanation here, but this doesn't work. 0 is not part of the domain, and I want you to see that early on. I'm just going to cross this off here. 0 just doesn't work. You can't plug in 0. In the same way, if you had an exponential function, I'm going to put this right below it, 2 raised to the x, this y value right here could never equal 0, right? Because just like in the warm-up, we had an asymptote at 0. So the graph was getting closer and closer and closer to 0, either working our way to the left or to the right, but you could never equal 0. Okay? In this case, the log function, the x value, can never equal 0. We can't plug that in. It's just not part of the domain. Okay, so continuing on, what if we plug in 1? Well, this should work, right? Because we're asking ourselves the question, 2 to the what is equal to 1, right? Well, 2 to the what is equal to 1. Well, that's going to be 0, right? 2 to the 0 is equal to 1. Therefore, we do have this point. If I were to plug in 1, I would get 0 in this function, right? From right there. Okay, so I have 1 point. I can plot that. 1, 0 right here. Now what if I plug in another point? Let's plug in 2. Well, now we're asking ourselves, I'm going to write it back in log form now, right? I'm asking myself the question, log base 2 of 2 equals what? Question mark. In other words, 2 to the what is 2. I have to evaluate that. 2 to the 1 is 2. My answer here is 1. So therefore I have another point, 2, comma, 1. Okay, so now I can plot that, 2, comma, 1. I could keep on going here, right? I could plug in 3, but you would see that 3, I'd have to use a calculator or approximate that. The next quote-unquote good point to use would be 4, right? Because if I plugged in 4, I could figure out that. I could say, what is log base 2 of 4? What does that equal? right? That has to be 2. 2 to the what is 4? 2 to the 2 is 4. So I have another point, 4, comma, 2. 1, 2, 3, 4, and I got one up here. Think about for a second what the next good x value would be. The next x value that would give us a nice whole number. Right? And if you think about that, right, that's going to be 8. Because 8 is a power of 2. Right? Log base 2 of 8, 2 to the what? 2 to the what is equal to 8? Well, 2 to the 3 is equal to 8. So I have the point 8, comma 3. So 1, 2, 3, 8, comma 3. So what does this graph look like? It looks like this. It kind of goes up, and it doesn't level off. There's no asymptote up here. It just keeps going up, but it slows down its increase. And then what happens right here? Well, remember, we know that we cannot plug in 0. So there is an asymptote here. There's an asymptote at 0, but it's not y equals 0, it's x equals 0. So I'm going to have not a horizontal, but a vertical asymptote in my graph, again, which is not part of the graph. It just shows a boundary of the graph, or a place where the graph can't actually reach. So I'm going to put a vertical asymptote here. And with the vertical asymptote, we know that the graph is going to approach that line closer and closer and closer. So this blue graph is going to come this way, and it's just going to come down and get closer, but never reach 0. So that's what the graph looks like. And so if we think about this, we could say my domain is not all real numbers here. My domain is x has to be greater than 0. But my range is all reals here. And so you might have been getting some of these hints that a log function is an inverse, or it's like the opposite of this exponential function that we, just like we graphed in the warm-up and we did in 7, 1, and 2. They are inverses of one another. So when I put this comparison here, these two graphs right here, this one and then y equals 2 to the x, these are inverses. Notice that the points that we got, remember what an inverse is. An inverse just switches the x and the y values. Think about if I wanted to graph y equals 2 to the x. Think about the points that I just graphed to get my answer for this log. What if I switched the x and the y? Well, what points would I get? Well, if I switched the x and the y here, I would get 0, 1. And I'd get 1, 2. And I get 2, 4. And I get 3, 8, etc. Notice that the x's right here are all the y's on this one. And all the y's on this one are all the x's in this one. So they are inverses of one another. Okay? So what that means, again, is it's going to be a reflection. If you were to graph these two things side by side, let's go ahead and do that. If I were to graph the y equals 2 to the x next to this one, let's go ahead and plot these points that I put up here. Right? 0, 1 is right here. 1, 2, 2, 4, and 3, 8. It's like up here. This is going to be like exponential growth. It's going to go up fast, and it's going to level off down here. Okay, notice the relationship there. We have a reflection that we saw before in another section between this y equals x line. In other words, this line right here in the middle, if you were to take your paper and fold it over that line, you would get those two graphs basically being smashed right on top of each other. Right? So these two things have an important relationship here, and everything's going to kind of be switched around. So notice that, I'm going to put this in blue. For my log function, the domain and range is the exact opposite of the domain and range for the exponential function. Normally, if we go back to, this warm-up question, we'd say, oh, the domain is all real numbers. It goes all the way left and it spans all the way right. But if I go to this question right here, we'd say, no, the domain isn't all real numbers here. The range is all real numbers here, right? So that's one connection that I want you to make. Now we're going to learn how to graph these log functions a little bit more efficiently. And to do that, we're going to look at the general form. So for the general form, we're going to say that is y equals a log, and we're going to say a base b of x. So we have some base, we have some input, right? Now this is like the base function. Now the parameters that we're going to add on to it is we're going to have a multiplier like we would any function. So we're going to put a times that out there, and that'll have some sort of effect on the graph. But we can also have a horizontal shift like we always would, because we can put a minus h there. Right? We can have an h value, and we could have a k value. Right, so no matter which function we've done, quadratics and we've done exponentials, the same pattern happens here. This a value, this multiplier, is going to be some dilation or vertical stretch. This h value is going to be some horizontal shift, and this k value is going to be some vertical shift. Nothing really changes. So again, if we look at Desmos, let's look at how these translations happen with the log function, just as it does with the other ones. So here's the log base 2 of x. This is what we just graphed in that example. And we're going to add all those things. We're going to add a h value, we're going to say minus h. We're going to add a k value, plus k. And so if I change the h value, right, you're going to have this horizontal shift going left and right with the same basic shape of a log function. If we have the k value changing, we're going to have a vertical shift. And if we add a value, let's just make an a value out in front, that's going to be a stretch. So if I make a bigger, you can see this is going to be a vertical stretch upward. And if I make a smaller, it's going to be more of a vertical compression. It gets smaller. Now a could go negative. If a goes negative, then my graph goes like this. And it decreases as we get further out instead of increases because it's negative. So another thing that we can show here is how the exponential function goes right along with it. So if I have another function, y equals 2 raised to the x, you can see the relationship between these two things is we have an inverse. And I'm going to match this up exactly. I'm going to put x minus h, and I'm going to put a plus k here, and I'm going to put an a value here, just so it's all the same. Okay, so no matter what a, h, or k is, notice that the black and the red graphs are going to be reflections of one another, right? You can see that they're inverses, and they do the exact same thing. They either have a horizontal or vertical shift. The a value is just going to stretch them out in a certain way, right? So I want you to see and visualize that as we go through this. Okay, so let's graph one of these. We're going to graph log base 3 of x minus 2 plus 4. We're going to state the domain and the range. So to do this, we're gonna make some key points. We're gonna just say, all right, what are my key points that I'm going to start with? And the key points we're going to start with are really just going to assume that we have the same function, and we're just going to strip away the h and the k values. So I'm going to assume this base function or parent function. In this case, let's get rid of the h and k, and so I'm just thinking about, what does log base 3 of x look like? What are those key points? And so key points here, our key points are never going to start at 0, because remember, 0 cannot be plugged in. The key points are always going to be 1, comma, 0, right? If I plug in 1 into this function, any log function, the log base anything of 1 is always 0. So 1 zeros in this situation is going to be a key point. And the next one I'm going to plug in is the actual base. So you can see the base here is 3. Well, what if I plug in 3? What's the log base 3 of 3? Well, think about that. What we've talked about so far, that has to be 1. These are just two quick and easy points that we can use as our base function here. And remember, we're going to have a vertical asymptote always of x equals 0. So if I were to graph this base function, which is not my actual answer, but just to kind of show how we start, those are my first two key points. If I plot 1, 0, I have this, and then 3, 1 is right here, and I have a vertical asymptote right here. Let me try that again. Vertical asymptote, our dotted line, and if we graph that, it just looks like this. It's going to increase, it's going to go up and to the right, and then come down and get closer to our asymptote, not quite reach there. There's our base function, and we're going to take that base, those two key points, and we're going to translate them. We're going to now think about our h and our k values and how that changes things to our new points. So my two new points now, right, my h value in this case is 2. So I'm going to add 2 to each x value. I'm taking whatever I have for the x value here, and I'm going to think of this as x plus 2. And my k value is 4. So I'm just going to add 4 to all the y values. So this is going to be like y plus 4 for these new points. So my 1 for my first point now becomes a 3, because I'm going to add 2. And my 3 becomes a 5. And then for the y values, my 0 is everything is shifted up 4. So we go 4. And then the 1 becomes a 5. So again, the visual here, if I take this base function, I am shifting everything to the right 2, 1, 2, and everything up 4, 1, 2, 3, 4. And there's my new graph. And it should match up with these points that I already have, 3, 4, and 5, 5. Now the asymptote also changes. It's not x equals 0 anymore, it's x equals 2, because I'm shifting everything over to the right 2. So even this asymptote shifts over to the right 2, 1, 2. The process here is almost identical to the graphs we just did with exponentials, except everything's kind of flipped over on its side because it's inverse. So as long as we can just plot that, base function, and then we can still use our a and our h and our k values to get our new values, we're doing the same thing. Now this problem says to state the domain and range. My domain here is x is greater than 2, and my range is all reals. All right, if you feel like you got your graphing down, you can skip over this question, but if you want just one more practice with these graphs, we'll do one more here. So again, we're going to graph this function using 2 key points and an asymptote. So we're going to make 2 key points. from this general form. Remember, the general form looks like this: y equals a times log base b of x minus h, and we have a k there. And all we're gonna start with is, let's just think about y equals 2 times log base 3 of x. Let's think about this function without the h and without the k value to simplify it a little bit, and then we can think about the shift left, right, up, down. So let's think about 2 points for this graph right here. Those 2 key points. The first thing I'm going to plug in is always 1. I'm going to plug in 1, and if I plug in 1 here, what do I get? I'm going to have the log base 3 of 1, which again is always going to be 0. If I plug in 1 into this type of function, I'm always going to get 0. And then the second thing I'm going to plug in is the actual base that I'm using. I'm going to plug in 3 into this function. So if I plug in 3, what's the log base 3 of 3? Well, you'd say, well, that's 1, right? Well, I have an a value here, though. The a value is multiplying everything by 2. So I'm going to have 2 times 1. So this is going to be 2 here. Those are my 2 key points for this parent or base function here. So, and of course, the asymptote for this is going to be x equals 0. So let's put that in here as well. X equals 0. So my graph is going to be 1, 0, and 3, 2, which is up here. And there's my base graph with an asymptote of x equals 0. So I'd have this line, vertical line right down like this. Okay, now what do the h and the k value do to my graph? How does that translate the points? So now if I take these points and translate them using my h and my k value, I can see that my h value is -4. So h is -4. My k value is 2. So that's going to be a shift to the left 4 and up 2. So my x value is really going to be just subtracting 4. And my y value is going to be adding 2 to it. So let's look at my key points. 1, 0 is going to become -3 and 2. And my 3, 2 is going to become -1 and 4. So those are my 2 points that I can plot now. So let's go ahead and take this. And again, I'm going to shift to the left 4. 1, 2, 3, 4. Go up 2, 1, 2. And those should be my new points. -3, 2 and -1, 4. And of course, the asymptote also changes. It's not x equals 0 anymore. It's x equals -4 because everything shifted to the left 4. So I have, there's my asymptote. And there is the answer to this graph right here.